So welcome. In the two parts of Bernoulli equation, we have seen friction factor, how to calculate that, and now what we are going to do, we have also seen some problems, and now what we are going to do is to look at a little bit more about this piping, and besides the pipe, what else is there, and why do we require all these things in the pipeline. So here is what we have done. So just a quick revision and some questions. We are on Bernoulli equation and applications of Bernoulli equation. That's where we are in the course. Just to quickly help you revise what is meant by friction factor, what are the two commonly used friction factors, how is friction factor and Reynolds number related, write Bernoulli equation in terms of head, and then revise the problems that we have done, right? And then we will see go forward. Okay, here is a next problem. I would like you to calculate the pump power, suction and discharge pressure for the various flow rates and pipe sizes. The situation is the same as earlier. Rho is 1000 kg per meter cube, mu is 0.001 Pascal second, length between 1 and pump, that means 1 and 3 is 5 meters, length between 2 and pump is 400, pump and 2 is 400 meters. It should be pump and 2. Length doesn't matter, length only that flow is going from 4 to 2, so we prefer to write it as 4-2. P1 and P2 both are atmospheric pressures. H1 is 0, H2 is 10 meters. Okay. What I would like you to do is calculate the pump power, right, suction and discharge pressure for various flow rates and pipe size. We have done this for 25 meter cube per hour. Pipe diameter, let's say we want to vary the flow rate and we want to find what happens to HP when we change the flow rate and what happens to suction and discharge pressure when we change the flow rate. So take flow rate 5 meter cube per hour, 10 meter cube per hour, 15 meter cube per hour, 20 meter cube per hour, 25 meter cube per hour, 30 meter cube per hour, 40 meter cube per hour, and do the calculations for a given pipe size. So pipe size you can take 2 inch, schedule 40. If you want, you can do this very easily in Excel. Okay. What I would like you to tabulate is, first of all, either you can change the flow rate and keep pipe diameter the same, or change the flow rate and keep pipe diameter the same. Let's do this first case. Flow rate is the same, pipe diameter we are changing. I would like you to find out what happens to HP and the pump power required. Okay. If you want to do this in Excel, here is how you can do it. I'm going to show you for one diameter. Okay, so what I have written, H2 is 10 meters, L13 is 5 meters, L14 is 200 meters. Flow rate, I want same flow rate, 25 meter cube per hour. So if we take different diameters, so 52.5, that's 2 inch pipe. Let's just put that here. So diameter in inches. So 2 inch. So velocity, if we calculate, we can calculate that from here. Flow rate is 25 meter cube per hour divided by 3600 meter cube per second divided by pi by 4 multiplied by 52.5 millimeters, so divide by 1000 and square that. So velocity will come out to be about 3.2 meters per second. Okay, Reynolds number we can calculate. Reynolds number is diameter divided by 1000, that will give you in meters, into velocity into rho divided by mu. Okay. Friction factor, if we calculate, let's say pipe is smooth, 0.079 multiplied by Re raised to minus 0.25, so that will give you friction factor. HF, just check this formula, 0.079 Re raised to minus 0.25. Yeah, HF is 2 F velocity square length is 5 plus 200 2f v square L divided by d. D is this divided by 1000 into 9.81 G HF. Right? So in terms of meters, about 31, we had got something 41, I think. That was because of the rough pipe. Okay, so this is now our HF. Now what is HP? HP for this particular case, in this particular case, remember P1 and P2 are same, V1 and V2 are cancelling out. HP required would be height difference plus HF. We had seen that in the previous problem. Let's go to Excel now. HP would be this plus 10 meters. H2 minus H1. Should put as H2. Right? I put it as formula because anytime these changes, all the numbers will change. HP. So now what is the power? Power is HP into rho into G into flow rate, 25 divided by 3600. That is power in terms of watts. Now if we do for other pipes, let's say 1 inch pipe, 4 inch pipe, 6 inch pipe. Right? So 1 inch pipe will be this divided by 2 approximately. Here 4 inch pipe will be this multiplied by 2. Actually you should take from the pipe sizes that we have talked about. You should take it from the table where we had 2 inch schedule 40 pipe. Take it for 1 inch schedule 40. Take this value properly. Don't take it as this number. Take this value for 4 inch schedule pipe. Don't take as this value. Take this for 6 inch schedule 40 pipe from the table, not this value. Now because in Excel it becomes so simple, we just have to copy this formula. Only thing we have to make sure is these numbers. So now this cell has changed, right? So we need to make sure that it does not change. Flow rate is what we want, right? Flow rate, it is referring to this cell, and if I copy the formula, it will change automatically. So we should do $B $5. Then diameter also be diameter is changing, right? Then Reynolds number, well, it is proper. Friction factor, it is proper. HF. Now the lengths, we don't want these lengths to change when we copy the formula. So $B $3, $B $4. Okay. HP, H rho G plus now this H2 height also we need to lock it, and then this is also need to be flow rate. So it is $B $5. Now if we calculate, if we just copy, everything will change automatically. So velocity has become 12 meters per second in this particular case. Let's just expand, just make it bigger. 12 meters per second. Reynolds number, friction factor, power. So you see 59 kW if it's a 1 inch pipe. 2 inch pipe it is 2.8 kW. 4 inch pipe it is 0.76 kW. 6 inch pipe it is 0.693 kW. Now if we put all this, right, we can put all these values. Let's see how these curves look like. So if you change the pipe diameter, cost of power will keep on reducing because head loss is reducing. That's cost of power. Right? But if I take a 4 inch pipe or a 6 inch pipe, that's going to cost me much more than, let's say, a 1 inch pipe. So the piping cost is going to go up as the diameter goes up. That's the cost of piping. So we take a cost based on now we'll see in project economics as you go in your higher and higher years, how do I optimize this? Okay, so that means there is an optimum pipe diameter wherein we don't require too much power. At the same time, cost of piping is also not that much. So we choose an optimum pipe diameter. This somewhere here in this range. It's not exactly the point of intersection because it depends on economics. We will see that later. In your fourth year, you can see that it is not exactly this point because these costs are different. One is per year and cost of piping is for a one-time cost. So we need to apportion that cost of piping to 1 year. Then we can take it properly. So don't worry about that. Implication is that there is an optimum pipe diameter, and typical velocities, if you find at this optimum pipe diameter, typical velocities of liquids in pipelines is about 1 to 1.5 meters per second. You can choose your pipe diameter so as to keep velocity of around 1 to 1.5 meters per second. But remember, pipes are not available in all sizes. If you take 1 to 1.5 meters per second and you get a pipe of say 39 millimeters, nobody is going to give you a 39 millimeter pipe. Either you have to go to 3/4 inch pipe, or you have to go to either you have to go to 1.5 inch pipe, or you have to go for a 2.5 inch or a 2 inch pipe. So you have to be careful in choosing the pipe sizes. So this is what you should be able to calculate from your own calculations. Next, now we can keep 2-inch schedule 40 pipe and change the flow rate. Let's see how this looks like. Remember, our HP pump power is equal to H2 minus H1 plus HF. Everything has cancelled out. Velocities are cancelled out. Right? Velocities have cancelled out. Pressures have cancelled out. Only height difference, potential energy, and this remains. So if you plot HP versus this flow rate, let's see how this looks like. We can even again do it very quickly in Excel. Right, let's go to Excel and we can see this for ourselves. So I've written the formula now. If I have to do for different flow rates, all I have to do is just copy these things. It becomes so much easier. You see, as the flow rate goes up, power required goes up. That's because the frictional loss is increasing significantly. So if you plot with respect to flow rate, even if the flow rate is 0, so if flow rate is 0, HF is 0. Okay? And then as flow rate goes up, HP will keep on increasing. So this corresponds to the H2 that is required. And you will see that it is exponential, it's not exponential, it's really quadratic because it is V square or V raised to 1.75 dependence. This is called as a system curve. Okay, we'll see the implications of this when we start doing pumps. Okay, same way, if you change the flow rate, now calculate P3 by rho g and P4 by rho g. So even if the flow rate is 0, P3 by rho g, if I plot, P3 by rho g will be some value. P3 will be equal to atmospheric pressure. There is no flow, so there is no head loss between P1 and P3. P3 will be equal to atmospheric pressure. So this will be atmospheric pressure divided by rho g. You calculate these values for yourself. Use Excel. Only then you will be able to be very clear what we are talking about. And as you increase the flow rate, the head loss increases. This will go down. Okay, we are only plotting P3 right now. P4, same way. P4 will keep on increasing from 10 meters as we keep on increasing the flow rate. Okay, now just one thought, as P3 will reduce, what happens if P3 is equal to vapor pressure? If P3 is equal to vapor pressure, that means what will happen is this P3 is equal to vapor pressure of water. If that happens, then water starts boiling, vaporizing here, and vapors enter the pump, and then pump will not work. Why pump will not work is something we will see as we go along. But we want this pressure, suction pressure, to be always more than vapor pressure. Let's write that. I want this suction pressure, or rather than talking about suction pressure, we talk in terms of P3 by rho g, and this P3 by rho g we will call as suction pressure divided by rho g. We will call this as suction head. Suction head. We want this P3 to be larger than vapor pressure because I don't want to boil water, I don't want to vaporize water, I don't want vapor to enter the pump. It will cause cavitation. We'll talk about it as we go along in our pumps lecture. So this P3 minus P vapor pressure, or PSAT if you want, this has to be always positive. So this is called as positive suction head. We don't want it to become zero. We don't want it to become negative. We always want it to be positive. And we call it as net because that is what is available to us. So this difference is called as NPSH, net positive suction head. So when we take a pump, we need to make sure that the piping is such that NPSH available based on this formula is more than what the manufacturer is telling us. So if you see some pump catalogs, you will see NPSH values. You want the piping and the location of the tank and the pump to be such that it has to ensure that P3 minus vapor pressure divided by rho g is always positive and it is always more than what the manufacturer of the pump is recommending. It's called as NPSH. That's why this is very important. Okay, do these problems for yourself. Okay. Now suppose, here is the problem once again. This same problem, now suppose what we are going to do is I am going to tell you that I am using a pump which gives 2 kW of power to the fluid, 2000 watts. And I would like you to calculate what will be the flow rate that will go from 1 to 2. Same problem as earlier. Okay. Do this yourself. Pause the video, solve. Okay, here is the answer. So if we write Bernoulli equation and simplify, you should be able to get this. We have been using this for a long time now. Now only thing is I don't know the flow rate, but I am telling you that pump gives 2000 watts of the power to fluid. So what is HP in terms of flow rate? HP rho GQ is the power delivered to fluid. That's 2000. So HP would become 2000 divided by rho GQ. So I can substitute that here. 2000 divided by rho GQ must be equal to H2 plus this HF, 2F V square L by dg. And if we take smooth pipe, we can substitute that. Now everything we know here. So 2000 rho we know, G we know, H2 we know 10, D we know, rho we know, mu we know, D is known, G is known, L is known, D is known here. The only unknown is this flow rate. So solve it, let's say using Excel or a calculator. That is what flow rate will come. You will get an answer in meter cube per second. Do this for yourself. Compare your answer with your friends. So I am giving you now the how much power. So again, go back to our first lecture. Head or flow rate, geometry and power required. Now what we were doing so far, I told you the flow rate, I told you the geometry, and I asked you to calculate the pump power required. Now I am giving you the power, energy, I am giving you the geometry, pipe sizes, and I am asking you to calculate what flow rate will go through. So you remember that triangle, flow, geometry and power, or flow, geometry and energy. Any two out of the three I know, third one we can calculate. Here's another problem. Suppose I use a pump that gives HP as 70 minus 0.015 Q square. Okay? And here Q is in meter cube per hour. That means that pump doesn't give a fixed amount of power. The power or head that the pump develops depends on how much flow is going through. Why this is the case, we will see little later on, but this is very important point. The pump develops a head according to how much flow goes through the pump. So in this formula, Q is in meter cube per hour, HP is in meters. Okay. Same problem as earlier, everything is the same. Density, water, viscosity same. 2 inch schedule 40, 200 meter, 5 meter pipe, P1, P2 atmospheric, H1 0, H2 10. I would like you to calculate how much flow will go through this pipe. Pause the video, solve for yourself. Okay, here is the answer. So if we have been using this, HP is equal to H2 plus HF12. Now HP is not a fixed number, it depends on the Q itself. So it is 70 minus 0.015 Q square, and remember this Q is in meter cube per hour and HP is in meter. So I can substitute that here. H2 I know, 2F and all the things I know, same as last time. Only thing is this Q now is in meter cube per hour. If I have to convert to, see here Q was in meter cube per second. We have taken Q to be in meter cube per second. Now Q is in meter cube per hour. So I will need to divide by 3600 so that I can get it into meter cube per second. Then I will get velocity divided by pi by 4 d square, velocity in meter per second, and then the head loss due to friction HF will be in meters. This whole thing will be in now meters. And now you can solve for Q again. Okay, use Excel. That's why I showed you how to use goal seek, or you can use a calculator. Most of the calculators nowadays allow you to solve equations, one in nonlinear algebraic equations in one variable. Okay. Solve it for yourselves. Then only go forward. Once you are sure that you have got the answer and you know exactly how to do it and all the doubts are clarified, then go forward. Okay, here is the next problem. Suppose I don't have a spherical, I don't have a cylindrical pipe, but I have a pipe inside another pipe, so two pipes, and flow is happening in the annular section. Or I have a pipe with a square cross section, or I have a pipe with a rectangular cross section. Why these are important is because when you say for example ventilation systems, they typically have square pipes or rectangular cross section pipes. If you have seen AC ducts in buildings, they are typically rectangular or square cross section. Or sometimes I have flow outside a bundle of tubes. This you will do in third year. How do I calculate the friction factor? How do I calculate the head loss for that? Okay, so the way to do that is here. So if you write force balance, tau W into pi dl for a circular pipe would be delta P into pi by 4 d square. This will give you delta tau W would be delta P by L into d by 4. Or if you write in the force balance, tau W multiplied by wetted perimeter, so pi dl is the wetted perimeter, or pi d is a wetted perimeter, not L, so pi d is wetted perimeter into L, and delta P into cross sectional area. Pi by 4 d square is the cross sectional area. So this will give you tau W would be delta P by L multiplied by cross sectional area divided by wetted perimeter. So now if I compare this and this, d by 4 will be cross sectional area multiplied by or divided by wetted perimeter. So for non-circular pipe, we define an equivalent diameter as 4 times cross sectional area divided by wetted perimeter. So if you have flow through annulus, that is this particular case. Okay. Equivalent diameter would be 4 times flow area. Flow area would be pi by 4 outside diameter square minus inside diameter square. So these are used in double pipe heat exchangers. We will see that in semester 5. Divided by the wetted perimeter. Wetted perimeter is pi and d naught plus di. So then if you simplify, equivalent diameter will be just the outer diameter minus the inner diameter. And same thing for a bundle of tubes. You can derive this yourself. If it's a square cross section, let's say L is the side of the square, what will be the equivalent diameter? Equivalent diameter would be 4 times flow area, 4 times cross sectional area, 4 times L square divided by wetted perimeter. Wetted is 4 times L. Wetted perimeter is 4 times L. So this will just be equal to L. Okay. So that's how we can calculate equivalent diameter for different cross sections and use this equivalent diameter for all the calculations of Reynolds number, of friction factor and so on. Velocity will still depend only on the cross sectional area. If cross sectional area is this, velocity will be flow rate divided by this cross sectional area. It is not going to be based on equivalent diameter. Only Reynolds number you are going to calculate based on this equivalent diameter. In this case, cross section, square cross section, velocity will be flow rate divided by cross sectional area. Cross sectional area will be L square. That's how velocity you are going to calculate. And then in the Reynolds number calculation, you are going to use the equivalent diameter. Okay. Now, next thing is in pipes, it is not just a plain pipe. There are sometimes you need to join two pieces of pipe together, one smaller diameter and one larger diameter. You need to go around the corner. Let's say you're going to around the corner of a building, so you need a bend or an elbow. You need orifices, restriction orifices to be put inside. We'll see that as we go along. You need different types of valves, you need different types of flow meters, you need to have nozzles, T-joints, couplings, and so on and so forth. So these are called as pipe fittings. Now these pipe fittings cause additional head loss over and above, additional frictional head loss over and above what is there for straight pipe. So for example, if you recall, for a pipe we are having HF as delta P by rho G. Now we define a head loss coefficient for a fitting in the same way that how much pressure drop it causes. So if I measure pressure difference between this point and this point, that is the pressure difference. So if I say P1 is here and P2 is here and flow is going along this direction, P2 is here, this P1 minus P2 is the pressure drop that is caused by this bend. So then we can define a head loss coefficient or a resistance coefficient for the bend as some multiple of half rho V square. So HF then would be K multiplied by V square by 2G. Just a multiply is like a kinetic head, just a multiplication factor. And then these values of K are reported for different types of fittings and valves. Okay. Or we can define in terms of an equivalent length. Equivalent length is what is the equivalent length of a straight pipe that causes the same pressure drop as that of a fitting. So if I say this fitting causes a pressure drop of some, say 100 Pascal, and that 100 Pascal is equivalent to, let's say, 10 meters of a straight pipe. So then we can say that the equivalent length of the bend is 10 meters. So that's how we can define equivalent lengths for different fittings, and then these are reported for different coefficients. And for valves, we define them by discharge coefficient or a valve coefficient. We will see that as we go along, perhaps in the next class. Okay, so these values of K are reported. Let's say we have flow going from a smaller diameter pipe to larger diameter pipe, then the K can be calculated in this manner. If flow is going from a larger diameter pipe to smaller diameter pipe, then K can be calculated from this formula. Okay. So if you think about a tank, we've seen all these things. See this tank. So flow is going from the tank suddenly to a pipe. So from a larger diameter to a smaller diameter, larger diameter to smaller diameter. And in this case, the larger diameter is very large as compared to the smaller diameter. So this is practically negligible. So the head loss coefficient for entry from a tank into a pipe, entry of a fluid from a tank into a pipe is 0.42. And the reason that happens is, if say this is the large pipe or large tank and there is a small pipe here, this is, we are looking at half of the pipe, this is the center line, okay, then flow goes like this. So here vortices are formed and that causes rotating packets of fluid, and that causes more friction and therefore head loss. If you think about it the other way around, here the fluid is going from a pipe into a tank, from a small area to a large area. So here it is going from a small area to a large area. So the head loss can be calculated from here. And if the large area is like a tank, this d is very large as compared to small d, then this is 0. So k is practically 1. So even when we say pipe, head loss coefficient for this is 0.42, head loss coefficient for this is 1. So this I have to add when I take into account the lengths of the piping. Right now what you can assume that these lengths are included in these head loss that happens, but I have to account for them. Okay, again, if this is a small pipe, this is the large pipe, then the flow goes like this. Here vortices are formed. Vortices are nothing but rotating, circulating packets of fluid. Remember the plane that we saw, plane went through a plume of jet and that created vortices. Okay, if it's a bend, then it will depend on the radius of curvature of the bend, and that's because of these secondary flow patterns that are generated. This is called as Deen effect, D-E-E-N, Deen effect. Okay, and then the head loss coefficient is related to r by d, the radius of curvature. Naturally, the smaller the radius of curvature for the same diameter, higher will be our head loss coefficient, say here. Okay. Same way, whatever fittings we use valves to control. So if you go to a pipeline, if you go and see the pipeline, there will be several places where there will be valves which you can open and close to allow more and less flow to go through. So these valves are characterized in terms of valve coefficient, CV. And the way you measure that CV is you take this valve, you measure the upstream pressure, downstream pressure, this differential pressure if you measure, and if you measure the flow rate, let's say bucket and stopwatch, and then you can relate it in this manner, you can find out the CV, the valve coefficient for these discharge coefficient for these valves. And these are very important when you start sizing these valves. What size of valve do I need? Okay, there are different types of valves: globe valve, gate valve, angle valve, butterfly valve. What we will do, ball valve, plug valve, is we'll see a small video. There are standard symbols that people use when you're designing pipelines, and this is something we will see. But as you open the valve, you will have an experiment wherein you change the travel of the valve, which means you open more, say 10% open, 20% more open, 30% open, 70% open, 90% open, 100% open, and how the flow changes. These are called as valve characteristics. So these become very important when you start designing these valves, when you are specifying what valve I want in a particular pipe. So more about this later, not just now. So we'd like to see a video now that shows you different types of valves used in piping. You can see this video for yourself as well later. Just let us fast forward a little bit. Valve is used for controlling the flow rate. So you see the valve is opening now, fluid is going from left to right. So they are either, so this is more mechanical construction about the valve. This is different types of valves. We'll see that in this video. And what is the function? Whether I want to start, stop, I want to regulate, or I want to, so cast versus forged. Something about mechanical engineering, either it is cast or it is forged, means it is metal is taken at high temperature and pressed into a particular shape. That's called as forging. So this is very important. Different types of valves. So gate valve. So you see, when this valve opens, it's like a gate, circular gate, right? And it allows flow to go through. But even if you open slightly, a lot of flow goes through, so it's not a good for controlling the flow rate. It's good for on-off kind of situation, start and stop the flow. Globe valves, right? So these are the very commonly used valves for controlling the flow rate. So as you opening is created. This is called as valve seat, on which this valve body is resting. And as this opens, liquid goes through here. So you see now this liquid has to have a change of direction, and therefore a lot of friction is caused, a lot of vortices are caused, and a lot of head loss coefficient, a lot of head loss happens. Head loss coefficient for globe valves is very large, and therefore this can be used very easily to control the flow rate. But it causes pressure drop. Check valve. Now this allows valve. So you see now this valve is hinged here. It is opening. It allows flow to go from one to the other end, left to right. But if the flow comes from right, it will shut the valve. Flow comes from right to left, it will shut. Let's just see it again. Right. Flow comes from right to left. See, it will force this valve shut. So no flow will go here. So only flow will go from left to right. So that's why these are called as check valves. They allow flow only in one direction. These are called as ball valves. So you see there is a ball here, and this ball has an opening, and this opening right now is facing perpendicular. So the solid part of the ball is blocking the flow. No flow is happening. But when this ball rotates, this opening will match with the opening of the pipe and flow will go through. So again, these are used for on-off type. Means you can rotate or you can turn. Yeah. So this is a butterfly valve. So you see a gate that is opening it. The gate was going up and down. Here gate is just turning by 90 degrees. Again, so this is used for shut off and very little for regulation. So typically when you have air handling units, when you have ducts for air conditioners, and then you have you want to allow air to go in certain portion, you don't want to allow the cold air to go in certain portion, there butterfly valves are used. So that valve is rotating, it shuts the flow. So these valves can be so big, you see, used in petroleum industry. This is plug cock or a plug valve. It's like your burette. I'm sure you use burettes in your chemistry lab. It's like that. Safety valve, they release pressure. They open only when a particular pressure is exceeded. So if you set a pressure relief valve to 10 atmosphere, let's say, then if the pressure becomes 9 atmosphere, 9.99 atmosphere, it will be closed. But if it exceeds 10 atmosphere, say 10.1, 10.2 atmosphere, it will allow material to go out and protect the reactor or whatever the process equipment that you are having. Allow the liquid to go out, gas to go out. Strainers. Typically these are used before the pump, suction of the pump, to remove any dirt from the solid, from the water. If you see, especially in rainy season, a lot of dirt comes along with water that you get in your societies or in your houses. So strainers are used there so that pump doesn't get damaged, your piping does not get choked. Yeah, so this is the body, that is the outer part. It can be flanged or it can be screwed or it can be welded. Bonnet, this is the bonnet. It is hosting the stem. Trim is a collective name for all the replaceable parts that are in quarter. So the valve seat and actuator is this is the actuator. It is what is used to control the opening of the valve. Materials, you can be steel. So this is more now a little bit in terms of material of that valve, but okay, so you can see this video later on as well whenever your convenience. So these head loss coefficients are typically reported for different types of valves. So globe valve, gate valve, swing check valve, angle valve, elbows, T's, and the values of K are here. For a half inch, 1 inch, 2 inch, 4 inch, or flanged 1 inch, 2 inch. So you see, globe valve gives a higher head loss coefficient than a gate valve. Gate is just opening and closing. Swing check, this is in the forward direction, by the way. That's why globe valve is used for controlling, right? If let's say we take plug cock, okay, or a butterfly valve, 5% open, 5% closed, 95% open, head loss coefficient is small. 10% closed, 90% open, head loss coefficient is increasing. 80% open, head loss is increasing. 60% open, head loss is increasing. 40% open, it is increasing. So you see very dramatic increase. That's why butterfly valves you normally don't use for control. Whereas a globe valve, the variation can be more gradual. That's why we can use it for controlling. Or we could write in terms of the equivalent length. So for example, let's say a gate valve fully open. If it's a 1 inch gate valve, it will be equivalent to a 0.6 meters of a straight pipe. Okay. And you see globe valve. Globe valve will have a lot of equivalent length. So 1 inch or a 2 inch globe valve will be equivalent to 55 meters of the pipe. Sorry, this is in terms of feet. Sorry. So 2 inch, this is 55 feet, means like 18 meters. And there is one handbook called as Crane's handbook that gives data of all these various types of fittings. So people have related these values to the diameter and the type of valve. So these are correlations that are used, and there's an example here, and you can see how these are related, K and L equivalent and the valve discharge coefficients, how they are related. Not very important just now, but I'm just showing you just for complete understanding. Later on you can revisit and read this again whenever you need to deal with control valves, whenever you need to deal with fittings and so on and so forth. And here is one small problem. You can see this problem, you can read this problem yourself, pause the video and read this problem yourself, do the problem yourself. I'm asking you to compare different head loss coefficients for bend, R by D1, R by D4, means more radius of curvature, gradual, more gentle rather than a very sudden or a sharp bend, globe valve, gate valve, swing check valve. And you can see that globe valve gives a very high head loss coefficient. Gate valve gives a very low. If pipe bend is gradual, you get a lower head loss coefficient. So how we are going to incorporate in our calculations? Either we are going to say that HF is due to straight pipe plus head loss due to all fittings. So HF we can calculate in two ways. One of the way would be, so HF for the straight pipe. What is the straight pipe? 2F v square. By this time it should be very clear to you. You don't have, you would not want me to write 2f v square L by dg plus hf due to all fittings. So K, I can use K for the ith fitting, I say fitting 1, 2, 3, 4 and half rho v square. It is the velocity through that particular fitting. I may have different diameters in the pipeline, right? And then we need to add this all up for all the fittings. I have one fitting, second fitting, third fitting, fourth fitting, and so on and so forth. Each fitting I will need to add. This will give me delta P divided by rho G, and then rho will just cancel out. Okay. Or we can define total length, total if you want, as length of the straight pipe plus equivalent length of the fitting and of the ith fitting. And so we need to add this all up for all the fittings that we have. I have 10 fittings, I need to have equivalent length for all fittings, add them all up, add it to the straight portion of the pipe, and we will get the total length. And then this total length we can use in this formula. So then we will use just 2f v square L total d by g, right? So either we talk in terms of equivalent length or we talk in terms of the head loss coefficient. So this is how we would use all this. So this is what I wanted to cover in this lecture, and we will stop this lecture here.